Okay, our second speaker this morning is John Hauenstein with the second part of solving polynomial equations.
Thank you, Jan. So today's talk, we'll talk about isolated solutions first. How do we use homotopies to compute isolated solutions? What's sort of the geometry behind positive dimensional solution sets, and how can we do computations on them? And then at the end, I'll talk about complexity of the solving approaches and how it relates to Smale 17 problem. So if you recall, we're going to take a polynomial system F. And let's assume that it's a square system, so the number of variables is equal to the number of polynomials that we have. The nice thing about square systems is it's sort of well conditioned. I can perturb the coefficients and my solutions will still exist. And the idea is to set up a homotopy plus t times g of x. You give me f. My goal is to construct g appropriately and now trace the solution curves. So we want to set up this and then trace solution curves defined by h equal to 0. The nice thing about this is each solution curve can be tracked independently, so we have a good parallelization of this solving approach. Okay, so the first thing we want to do is how do we set up g? And there's different approaches, and let's start with the most basic choice of setting up g. And this is what's called a Bézieux homotopy. So Bézieux here corresponds to Bézieu's theorem, and it'll be generically sharp with respect to Bézieu's theorem. So assume that di is the degree of fi. And now I'm just going to take my homotopy to be very simply 1 minus t plus t times the following system, x to the d1 minus 1, x1 to the d1 minus 1, xn to the dn minus 1. So my g of x is this very nice simple system here. What do we know about g of x? Hopefully we can all write down the solutions to it. It should be clear. So g of x equal to 0 has d1 times n times dn solutions. They're all non-singular. Everything is nice about g. What's the problem? As I originally have it formulated, suppose f has coefficients which are real. This system has coefficients which are real. The real numbers cause some issues. So we want to take advantage of the algebraic closure of the complex numbers and add in some complex number here, where gamma is a complex number. We have to move away from the reals to the algebraically, their closure, the complex numbers. Good? And so now we can prove a theorem that for all but finitely many.
Sorry, why do you need the gamma?
So if we don't have the gamma there, think about f here having, let's say, x squared plus 1 is our f. And now we want to deform from x squared minus 1 times 1 minus t plus t times this. This has real roots. This has complex roots. The only way to get from real roots to complex roots is to pass through a singularity. And
I see. You want to avoid singularities on your path.
Exactly. Very good. Okay. And as you will see here, that's one of my statements of the theorem. So for all but finitely many points on the unit circle and complex numbers, the following things hold. One, there are d1 through dn continuous solution paths. Let's say x such that. All right, let's move to the other side of the board. What would be nice properties of this? Well, the first thing we would like is they should satisfy our equation. So for all t in the interval between 0 and 1. The other thing that would be nice is if they were smooth. So this example that I wrote up here for Jm, I believe had a singularity at t equal to 1/2 that I've now erased. So we would like these to be smooth so that the condition number is finite along the path, and so we can nicely trace along them. However, we have no control over what happens at t equal to 0 at f. So the only thing we can say this is for the open interval, open on the left side at t equal to 0. We have no control over f. You gave me f. I don't know what the solution is. I picked g so that at least away from 0, everything is nice. Good. What else would we like? The next thing that we would like is to look at the set of endpoints. Such that x sub t is solution path, and the limit as t goes to 0 actually exists. Okay? So maybe it's helpful to draw a picture. This picture is morally correct, but not mathematically correct. So here's my t, and here's my x space. Over here at t equal to 1, I have the roots of unity with their appropriate choices. And then over here, I don't know what I have. I have some points, I have some curves. I don't know what I have. And now I have these nice, smooth, continuous paths which sort of, I don't know, come over like this. And maybe some go off and diverge to infinity. So this is the morally correct statement. So if I look at the set of endpoints, the limit points, which converge in my affine space, what would we like to be true? We would like to be true, remember this is the isolated points, the isolated solutions. We would like this to be true, and indeed it actually is true. So the set of endpoints contains all of the isolated solutions, and obviously every endpoint is also a solution in my system. Something stronger than this is actually true. And in fact, E contains a point on every connected component.
Not algebraic component, but connected components.
Exactly. So it's not irreducible, but it's the connected components in the Euclidean topology over the complex numbers. So here I drew a sort of some kind of connected piece. I'm going to at least find one point on that connected set.
So if there's an embedded component, you won't necessarily find it.
Exactly. So as we talked about yesterday, if I have x squared and xy, I'm guaranteed to find a point on the line x equal to 0, but I may or may not find the embedded point.
And if you have two intersecting lines, all you're guaranteed is you'll hit one point on one of the two lines.
Exactly.
Only one.
Maybe one, maybe more. I don't know. It all depends upon sort of your choice on the start system, where it ends up. Okay?
What happens if the system has no solution?
Then all paths go to infinity. So if this system had no solutions, let's say x and xy minus 1, all the paths will go to infinity. What else would we like to be true? Suppose x star is indeed isolated, an isolated solution. How many paths would we like to converge to x star? The number of paths let's call it ending at x star is exactly the multiplicity of your system at that point. So if you have a multiplicity 2 root, for example, let's say I want to solve x squared. And I start with x squared minus 1. Here I don't need a gamma. Gamma is equal to 1 works here. You can rewrite this as x squared minus t. And now you can simply draw the picture. At t equal to 1, I have 1 and minus 1, and both of these converge to the origin. So, x squared has a multiplicity 2 root. I have exactly 2 paths converging to it. Okay, so that's the end of the statement of the theorem, and it's true. And people have brought up many concerns, and so let me address some of those. If my system has no solutions, then all of my paths will diverge to infinity. How do I track a path that has infinite length? My computer cannot do this. I'll be long dead before my computer ever reaches infinity. So how do I do this? Well, I transform my path into a compact path by going to projective space. So compactify to yield finite length paths. So there was a homework problem that I'll talk about sort of to demonstrate. We have 2xy plus 3x plus 4y minus 1, and then y squared plus 5x plus 2y minus 3. And we correctly found out last night at the homework session that this has exactly 3 real roots. Okay, so now I set up my homotopy. xy t is f of xy times 1 minus t plus gamma times t times x squared minus 1 y squared minus 1. And so the picture, if you think of xy in C2 in this direction and t between 0 and 1, over here I have 4 points. Over here I have 3 points. I know that 3 of the 4 paths have to converge smoothly to those 3 points, and then the other one has to diverge to infinity. So now let's compactify this. So we want to go from C2 and embed that into P2 and see that we can turn this infinite length path into a finite length path. All right? So now let's say that x, y, and z are my coordinates in P2. 3xc plus 4yz minus c squared, y squared plus 5xc plus 2yz minus 3z squared, 1 minus t plus 1 times t, x squared minus c squared, y squared minus c squared. Since this is a compact space, all 4 of my paths have to be compact. And so the picture looks exactly like this. Here's the t, here's the x, y, z. And can anyone tell me what the point at infinity is? Yes. It's the point 1, 0, 0. And so in the affine case, I was diverging to infinity in this direction. And so all I've done is I've compactified it. So now I explicitly see the endpoint is exactly the direction as I go to infinity. Okay? Good. So you avoid infinite length paths by compactifying things. And different compactifications lead to different types of homotopies. As we will see shortly, why did I compactify C2 into P2? Maybe I want to do C cross C and compactify this into P1 cross P1. And that exactly is a 2 homogeneous Bezout's theorem, which we'll talk about very shortly. Okay. So the choice of compactification will impact how well or efficient your method is for solving. Good. What are some other issues? Singular endpoints. Yes?
A priori, here you can say that because they are low degree and there is some arithmetic obstruction. But a priori, you don't know that path that goes to infinity goes at an isolated point, right?
A priori, I do not know, but plug in z equal to 0 and you see that it's isolated.
Here we can.
Right.
But a priori, we have paths that go to infinity. They can go to some positive dimensional component at infinity.
Exactly. And my theorem still holds if I switch from affine space to projective space. I get a point on every connected component at infinity, or every connected component over the projective space. And so if it lies at infinity, I get a point on it. Okay. So in this one, all 4 of the endpoints in projective space were nice, isolated, non-singular points. So I can use Newton's method to quadratically converge. Hopefully it was demonstrated in the homeworks, the power of Newton's method. Quadratic convergence is very powerful. Singular endpoints, don't know what's going to happen. I could diverge, I could linearly converge, I don't know. So how do we handle singular endpoints? So how to compute? Compute the endpoint when the Jacobian is rank efficient. All right. And the idea is to stay far away from the ill condition. It's only singular exactly at t equal to 0. So if my t is positive, I'm in a nice, well-conditioned region, except in the middle. So here's my t, and now I'm thinking of t as a complex number. At t equal to 0, I have a rank-deficient Jacobian. Everywhere else, my Jacobian is full rank. So can I use things in this well-conditioned region to approximate an ill-conditioned answer? Has anyone seen things like this before?
Couldn't you just project in the space orthogonal to the where the eigen?
Yeah, so one way you can do is you can just track your path close and then sort of project in some direction. And what you know is that x sub t has a Poisson series expansion. Is that
Close enough.
I think there's an A somewhere in there, maybe. Close enough?
C-A-U-X.
EAUX has a series expansion, Poisson series expansion, in a ball containing t equal to 0. And of course, this is an open ball, as I've demonstrated here. So x sub t in this ball has a Poisson series expansion, and at t equal to 0 is where I want to find it. So I can do exactly what you suggested, sort of. So one option is to pick points in this ball. So i.e. compute x of ti for various I. Fit a Poisson series. And then evaluate at t equal to 0. Good.
You're assuming an isolated point.
No.
No.
No. The nice thing is it's isolated with respect to the homotopy, x of t, away from 0. But at t equal to 0, I don't know what happens. It could be isolated, it could be positive dimensional. Nonetheless, I have a Poisson series expansion there. So let's think back to the very simple homotopy I wrote down before. X squared minus t. One path was on the positive square root, and the other path was on the minus square root. And for those that don't know what Poisson series are, these are fractional Laurent series with a constant denominator. So here I have an actual power series in t to the 1/2. Good? So in general, x of t, and let's switch a marker. In general, x of t looks like this. Summation for j equal to k to infinity of a sub j times t to the j over c, where k is some integer. It could be negative. And c is a positive integer. C has a name, and this is what's called the winding number. So the winding number is a complex analytic number, which says that if I do loops around this, this is the number of times I have to wind around before I come back to where I started. So this should suggest something about Cauchy's integral formula. So either we have a Poisson series and we try and approximate it, or we could just go the route of using complex numbers. And do Cauchy integral. So this says that x of 0 is 1 over 2 pi c, integral from 0 to 2 pi c, x of r e to the I theta, d theta, for
0 to 2 pi I,
2 pi c.
or 2 pi c.
This is I theta.
Yes.
Yeah, good.
Yeah, sorry. 2 pi c. And for, I know this is true because it's on a small ball, so if my radius is sufficiently small, then I get this. Okay. So that's one way to approximate singular endpoints. And just so you know, these go by the name of endgames. What happens at the end of my path? Okay? After I've approximated these,
Question.
yes, go ahead.
How do you find the winding number we have before picking the series?
So one way to find the winding number is to actually do what I said. Do loops around it until you come back to where you started. The other way is just to think, okay, this winding number is going to be some positive integer, so I'm going to test at c equal to 1 and c equal to 2 and c equal to 3 and try and approximate it. If you have enough points, you can make a very good educated guess on what it is. It's a difficult question. One way you actually compute it by integrating around the curve. The other way is you just guess. Okay. Even if we can approximate our endpoint accurately, we would like Newton's method. Newton's method, the power of quadratic convergence there. So, how to restore quadratic convergence? Of Newton's method. So the idea is my Jacobian is rank deficient. There's extra conditions that are going wrong there. So if I add in extra conditions to my system to remove the singularity. So let me give you an example. And I hope everyone has seen this before. Univariate polynomials, a multiplicity m. What do you know about a univariate polynomial of multiplicity m? So in the univariate case, suppose that f of x star equal to 0 and the multiplicity of f at x star is m. Can I construct a new system such that x star has multiplicity 1? Hopefully you've seen this before. But I'm going to add a twist to it. Of course, you know that the m minus first derivative, it satisfies the m minus first derivative and it's not singular. But I'm going to add a twist to it and just keep all of the other derivatives. Start with the system I have, add the first derivative. Did that make it non-singular? No. Add the second derivative. Did that make it non-singular? No. Keep going until I've added the m minus first, and now it's non-singular. So now I know that g of x star is equal to 0, and the multiplicity of g at x star. The deflation methods.
But I'm a little
Go
confused
ahead.
with the order of events. So you're doing the method. It doesn't converge.
Yes.
So then what? So then you just start. Then you throw in all the first derivatives. And if it still doesn't converge quadratically, you throw in all the second derivatives? Is that what you're doing?
Exactly, but you add in rank conditions on the, so in the univariate case, there's just one derivative to add in. But in the multivariate case, there's directional derivatives to add in. So in this direction, this derivative vanishes, so I need to add that into my system.
But how do you know, okay, good. So that's exactly my question. How do you know which ones so all you know is that Newton's method is not converging.
Exactly.
So how do you know which derivative to which derivative?
So I go back to my methods to approximate my solution better.
Mm-hmm.
I know this will work, but I can't integrate things. I can only numerically integrate them. So now I use a higher order numerical integrator, compute this more accurately, and now plug it back into my system, find the derivatives which vanish, add those in. Did it work? No. Come back, compute more efficient, more accurately.
How do you
I
select
still
the
don't-
directions? How do you select
Yeah,
the directions?
that's the question.
Okay, so let me tell you the easiest
You
way.
also destroyed that it was square.
Of course, my system here is not going to be square anymore. It's going to be overdetermined.
Yeah, I'm not worried about that, but I just don't know how you
Okay,
pick.
so here's the easiest way to say this. Okay, and so this was a FOCM paper by myself and Charles Walker. Take F and say you have a good approximation to x star. So this is approximately 0. Now compute the rank of the Jacobian. So if I have a good approximation, I can use SPD to compute this. And so let's say this is R. So now I'm going to take my system, and I'm going to add in all the R plus 1 by R plus 1 minors of my Jacobian.
That's a lot.
That's a lot. But the nice thing is that you don't need all of them. You only need the codimension many of them.
On the average.
For explicit computation, you can pick which ones you need at your point you're interested in. And now
this
you
is how
take
you avoid picking a direction.
yes.
I see.
Yes. And now you iterate. This is my new system. Compute the rank of the Jacobian.
And the fact that these are very high degree doesn't bother your computer.
What bothers my computer is the fact that there's a lot of them.
More than that the degree is R times the degree.
Exactly,
F
because
of
all
X.
I'm doing is local computation there. I can efficiently evaluate each one of these minors and their derivatives. I don't need to expand them out.
So when you go to second and third and fourth derivatives, do tensors get actually used in tensor methods?
Not right now, but it would.
Could be.
You could be.
Structured tensor.
Yes, absolutely. So does that clear things up?
I'm fine.
Okay.
And the fact that this is overdetermined, doesn't it cause any problem?
No, because
Even that one.
there's a subsystem which is full rank, and that's all I need, is a full rank subsystem.
Or you just take a generic subsystem.
Exactly.
And we don't care that doing this we throw away all the other solutions. Because
Right,
now we
because
are only there.
I'm only interested in this particular solution. For your other solutions, you might have to do something completely different. Your multiplicity may be different, doesn't matter. But for this particular solution, how do I restore quadratic convergence of Newton's method for this one?
For the Newton iteration now, the derivatives it's not quadratic anymore. You take a pseudo-inverse, multi-inverse.
No, you take a random subsystem of this, which is the next
Okay.
the next thing.
Okay, I wondered how would the Newton iteration be? This one step.
So you could either take a pseudo-inverse of this, or you could take a random subsystem and then use that
Okay.
for your Newton's method. And you get quadratic convergence in both of them.
Okay, and then if you take a random subsystem, the multiplicity will be.
Yep. That's exactly my next statement here. So singular things naturally lead to overdetermined conditions because there's extra minors that vanish. So there's extra conditions that vanish there. How to handle overdetermined systems. Okay, so start with your polynomial g, your system g1 through gn, and x is x1 through xn. And now look at this system. A times g of x, where A is a n by n matrix. So now my f is a square system, so I can do all computations with f, whereas g is an overdetermined system. All right. And so now we're to Bertini's theorem. How do the solutions of f and g relate? And in particular to Peter's question, what about the multiplicity? So this is Bertini's theorem. So there is a Zariski open, dense subset of the n by n minors, n by n matrices. Let's call it U, such that for all matrices A and U, what's the relationship between f and g? Obviously, if I have a solution of g, a times 0 is still 0. So I know that this contains everything that I started with. What about the extra stuff? What happens to the extra stuff? It satisfies a randomization but doesn't actually satisfy my system. Consists of finitely many non-singular, and I have to tell you what it's with respect to, non-singular with respect to f solutions points. Solutions.
But I thought you would expect, other than, since this is so, oh, I see. Sorry.
Okay, so my system, my randomized system contains everything I had before, plus some non-singular points that are sort of somewhere lying out there. The more important thing is what happens to the multiplicity. Suppose I have an isolated solution of g, then the multiplicity, if x is in here, then the multiplicity of f is greater than or equal to the multiplicity of g. With equality, if either is 1. So if my multiplicity of my overdetermined system is 1, then the multiplicity of my random sum system will also be 1. So if either of these are 1, then you know the other one has to be 1. Or the multiplicity of f of x star is equal to 2. If this multiplicity is 2, this one also has to be 2. Okay, let's look at an example.
Why do they have to be equal if they're 2?
If the multiplicity is 2, then it's singular. and therefore it's singular with respect to G,
Because that can't be 1.
and
'Cause otherwise
singular
the other
things
one-
can't have multiplicity of 1. So it has
Well,
to
why can't it be high? I mean,
It can't be higher.
You have
why?
an inequality.
That's-
Because if you think of multiplicity
because
as
F is
F is
greater
a,
than.
Yeah.
yeah, F contains stuff in G
No,
plus
I
F.
got it.
Okay.
Sorry, a little dyslexic today.
Yeah.
Kind of like every day.
So let's look at this system, x squared, xy, y squared.
Just to know.
Yep,
the
go ahead.
multiplicity of f at x star is larger than 2?
Then
Then we don't know.
don't know. And this example will demonstrate. Okay, what is the multiplicity of G at the origin? 3. Very good. 1, x, and y are the standard monomials, and there's 3 of those. Take a random subsystem. I'm going to use notation like this. Well, let's just stick with standard notation. And here A lies on my Zariski open dense subset. What is now the multiplicity of F at the origin? 4. So my multiplicity is 4, and that obviously is the upper bound on 3, but not equal. Now comes a user-based question. For those that have used Bertini the software, which answer does Bertini give you, 3 or 4?
It's probably going to take advantage of the structure and give you 3.
Ah!
But I've never used it. It gives you 4.
Bertini gives you 4, because that is exactly equal to the number of paths which converge. Because this is a square system, this equals the number of paths, and that's what Bertini the software counts. How many paths converge? And so that's what Bertini the software will give you. So that's just a quick aside that if you have overdetermined systems, make sure you understand what the software actually is computing. Okay. Questions? Concerns?
So is there an issue in picking the A? I mean, maybe you might like to be interested in picking a somewhat sparse A.
Yes.
That's still, in some other sense, generic enough. What about the art of picking A?
So you can take, for instance, this. Reorder your G's so that you like the ones at the top and you don't care about the ones at the bottom. Now you can sort of randomize the ones at the bottom up to the top. And here, the same theorem holds on a Zariski open subset of the choice of matrices B.
That's simply because it only matters about the row space of A.
Exactly.
And you're just taking the Schubert sum.
Exactly. So you can add in structure onto your A's. You don't have to be completely dense matrix. You can add in lots of structure.
Well, I'm also thinking about pushing the number of paths down. Maybe if I locally, think about some Newton polygons or something like that.
Right. We'll leave it at that. Okay, so now let's return to Steiner's problem. So the question is, who remembers Steiner's problem from 2 days ago? A couple people. Okay, so it was count the number of conics tangent to 5 given general conics in C2.
Thank you. 3264.
Very good. I'll get to that. Okay, and remember, if I pick one conic, I have a hypersurface of conics tangent to that, and the degree of that hypersurface is 6. So this translates into a system of 5 polynomials. Here, x is in P5, and you can think of conics as equivalent to P5. And the degree of Fi is 6. So this is a square system. And so now you track 6 to the 5th, which is 7,776 paths. What happens to those paths? I know I'm going to get the isolated solutions. Because my space is compact, all of the other ones have to converge, and therefore they have to converge to the line, to the double lines. So if I can do arithmetic in my head, lie on the so-called double lines. Maybe I should just say is a double line. So these are honest conics tangent, and these are double lines which are fakely tangent because you have the multiplicity coming from the double line. So Steiner in roughly 1860 had access to modern 1848 had access to modern computers. You can do this computation relatively fast and see that the answer is not 7,776, but indeed 3260. This also proves that there are no other connected components. The only connected components in this system are exactly the double lines. Okay. So that's a nice application of Bézieux homotopy.
So they are all in the same component, all these
Yes.
4,500.
Yes.
But this then you see it if you compute it.
Right. You actually see that this one of these each of these conics is a double line. Right. It can factor as a linear square. Okay. So now Barrett sort of gave a hint that maybe you want to do some extra structure on here. Bézieux homotopies usually are not what you want to try. They overestimate the number of solutions very often. So typically, systems have a rich structure. And by that, the system F. And so you want to exploit that structure in your homotopy. If you think back to my, it's not exactly the same one, but close enough. Y squared plus 2x plus 3y minus 2. Doesn't matter. This wasn't the intersection of two quadrics. It really was the intersection of a curve of degree 1, 1 and a curve of degree 1, 2. There's really 3 solutions there on C cross C. So now I should be able to construct a start system times gamma, which has that same structure. So this is linear in x and y. So pick your favorite linear in x and y. X minus 1 times I minus 1. This is linear in x. So pick your favorite linear in x. And then quadratic in y. And so there you go. These both have the same 2 homogeneous structure. And therefore, my theorem at the beginning of the lecture holds. For all but finitely many choices of gamma, you get exactly what the rest of the theorem said. And now, hopefully, you see how to count. If I take x equal to 1, x is not 2, therefore one of these two.
Why did they take the cubic one back there? It's not on the left-hand side.
But so the degree of this is 1, 1, and the degree of this is 1, 2. And so I need 1 linear in x and 2 linears in y. So even though it's not cubic, as you would think of cubics, it is by degree 1, 2. And therefore, I need a polynomial by degree 1, 2. Okay. Okay, so this is multi-homogeneous. What are some other structures that you would like to exploit? Polytopes. I want to exploit the monomial structure of this system. So now instead of this start system, I create a new system, and I'll explain the notation in a second. So I'm going to replace this system here with this system. And each one of these boxes means pick your favorite random number. So I've taken my given system and thrown away your coefficients. I don't like your coefficients. I'm going to substitute my own coefficients. And I'm going to generate them from my favorite random distribution. Solve this system, and then track the homotopy paths over to here. Good. And so Bernd can tell you much more details about this than I can. How many points do you have to have over here? So the number of paths is equal to the BKK bound for your system. So the mixed volume of the corresponding Newton polytope. So you can use the combinatorics to compute this bound, and then use the polyhedral nature of this to compute the solutions, and then deform from there. Okay, where are we going? How time?
What if you have sort of determinantal type equations? Do you have a special thing for those?
So the art of homotopy construction is knowing how you constructed your system, so then you can construct a good start system. So typically, anything that you can find, anything which is a constructive bound on the number of isolated solutions. So if you have a constructive way to bound the number of solutions, typically you can turn that into a homotopy. So for determinantal things, there is a constructive way to bound the number of things. And so if there are problems of interest, generate the family of those. Though generically that will have that bound, and then therefore you can set up the homotopy.
So the problem is solving one instance.
Yes. So there's two problems. One is counting the bound. So how do you actually compute this bound, for instance? And then the other thing is, how do you actually find the right number of solutions to this system that agrees with this? And then you can do the homotopy. So this is the art, and systems that many of you generate have lots of structure. And the art is finding that structure and being able to exploit it. There's a lot of room for generating special types of homotopies for your system to visualize. Yes?
How is the randomness helping you?
The randomness is helping me here that this will have all of these solutions, because I have the constant term here. I know this is true. All of these solutions will be non-singular and isolated. And so therefore, my homotopy paths will be smooth, except at the very end, possibly at the very end. So the randomness is guaranteeing me this non-singular solutions at this system.
It's guaranteeing also that this system is well posed.
Yes. Yes.
So this is another important issue in numerical analysis.
Absolutely.
With high probabilities.
Of course.
These are guarantees, not like unconditional.
Right. With probability 1 based upon your reasonable choice of random numbers.
It seems like the new system that you created is harder potentially to solve than the one that you started with.
And Frank pointed this out. That's the art. So what did Bernd do here? He deformed to sort of binomial systems. Binomials are much easier to solve, and then lifted back to solutions here. So that is also the art. How do I solve this system?
Well, you might as well just deform your original system then.
But this could have singular solutions, this could have positive dimensional components. At least I'm deforming to a solution that I know is nice.
So what if you pick, let's say, your 4 favorite points, and then so that you know the solutions of the other system, and then choose your coefficients which vanish at those.
Absolutely. That's
that
right. Why did I
The
pick?
easiest way.
Why did I pick this one? Why can't I pick, so A1, B1, BI for I equal 1 to 4, and then find the 2 polynomials that vanish at exactly these 4 points? They're equivalent. So, absolutely.
Yeah. Well, it's actually extremely easy to find, given a solution, to find a system of the structure you want that has that as a solution.
Absolutely.
And that's also a method that people are thinking about.
Yes. So my favorite homotopies right now are Newton homotopies. Pick your favorite y, and at t equal to 1, I have a solution. And now I can deform from y along my curve. So it's very easy to write down a homotopy, pick y, write down a homotopy that vanishes there. You can also do what are called fixed point homotopies. And
I don't understand.
I don't understand your doing
F of x minus t f of y.
y is a fixed point. I pick y star first,
Oh,
and then I construct this homotopy. And when t is equal to 1 and x equal to y star, I have a solution. You can also do plus t times x minus y star. And again, when t is equal to 1, y star is a solution of this, and now I can track that path. I don't have, in this case, at t equal to 1, there is a unique solution. But in this case, there could be multiple solutions that I don't know what they are a priori. I'd have to compute. Good. So let's get a different pen.
So just a question
Go ahead.
about your nomenclature.
Yes?
Why is that called Newton homotopy?
This has been asked several times by several referees.
On the same paper?
Different papers. And the reason is, the best answer I can give you is there are some classical papers in engineering that call these Newton homotopies. And therefore, I'm sticking with their name. That's the best answer I can give you.
gotta call it Hauenstein, Rosen.
From what time? Are those old papers?
From roughly the 60s?
From the 60s.
Yes. So that's the best answer I've given the referees who've asked.
And the fixed point?
That's a similar thing. These have been used for 40 or 50 years, and they just sort of got the name afterwards. Okay? I shouldn't have erased this. Honest. All of these homotopies that I've written up are all in a general class called coefficient parameter homotopies. And the idea is, if I can solve for a sufficiently general point, then I can change either my coefficients or some other parameters and solve at the system that I want. So here, my parameter space is the set of all bivariate polynomial systems where the first polynomial has degree 1, 1, and the second polynomial has degree 1, 2. So this is really a homotopy inside of that space. The same thing with this. This is a homotopy in the set of polynomials with the same monomial structure. And you can sort of generalize this. So if I look at Steiner's problem, suppose I solve Steiner for my conics C1 through C5. I know there's 3264 solutions. And now suppose I want to solve for new conics C1 prime through C5 prime. I can deform in the space of conics from the solutions to this to the solutions of this. And I only need to track the right number of paths. So here, I'm going to have a generically sharp homotopy that consists of 3264. Is that the right number?
Yes.
Okay.
So why do you know you're not going to have to pass through a double line?
Ah, very good. You're going to take a general path in your parameter space, and the only way you can end up at a singular point is if your conics were degenerate. So with probability 1, the path between these two will not pass through a singular point.
But now this feature is a little different from the previous one in the sense that it's no longer linear. T is not linear,
Exactly.
but of order 6.
Exactly. So here, I really have a nonlinear parameter space that I'm moving through. Over here, I have a linear parameter space, the linear affine space given by these 8 coefficients.
Why are those nonlinear?
Because it's a discriminant. So for two conics to be tangent is 6, 6.
Oh, right. It's a degree 6.
Yeah.
Sure. Gotcha.
Yes, thank you.
Okay.
So everything you would like to hold for linear spaces also holds for irreducible parameter space. And as long as you can stay inside your irreducible family, all the theorems I've said will hold with proper respect. Good.
Should we keep time for discussion?
What time did I start?
Quarter of.
Okay, I still have plenty of time.
The ending in -5 minutes.
Oh, sorry. Okay.
Minutes into the discussion.
Let me end with this. My apologies. I was hoping for this. At least let me state Smale's 17th problem. So the idea is I want a deterministic procedure for computing a root of a system in polynomial time on the average. Okay, what does it mean to compute a root? It means to compute a point in the quadratic convergence zone of Newton's method. Okay? And if you replace deterministic here with uniform, probabilistic, this has been solved by Beltran and Pardo. And if you keep deterministic, I believe the best is n to the log n, where n here is the input size. And this is by Bergieser. Please forgive me as I misspell your name.
But he could probably tell you the correct correction.
It's an I, not a D.
If you write it messy enough, you can't tell what it is.
Worse.
Okay, I'm done. Thank you.
Questions?
What do you mean by polynomial time on average?
What you can think of this is the number of steps my path tracker has to take is polynomial in the input size.
What do you mean on the average?
Pick your favorite probability on the set of polynomials with a fixed degree.
There is a fixed probability, it's Smale's favorite probability.
Okay, but the original statement of the problem did not say use this probability space. But pick your favorite or Smale's favorite probability space on the polynomial system. And then on the average, you can track this path in polynomial time.
So going back, maybe rewind 15 minutes when people were talking about the polytope, homotopy, and so on. If I give you a arithmetic circuit, or I draw the circuit, for instance, that computes a given polynomial, can you then design a better homotopy knowing that's the way I'm going to evaluate my polynomial?
In theory, you would like to. How to do it in practice, I think, will be problem dependent.
Well, also is the number of solutions understandable from the circuit?
Yeah.
I mean,
So just have in mind that I have a lot of my favorite types of polynomials that I never write them down.
Exactly.
But I know how to evaluate them, and I can tell you how to evaluate them. And it sounded like what you said is if I have a method to tell you how to evaluate a polynomial, then you can design a homotopy to help.
What you have to do is have a method which you can solve a polynomial in sort of the same class of those polynomials.
So you mean if I tell you a root of that polynomial in addition to telling you how to evaluate it?
No, the structure of that polynomial system.
If you have a program to evaluate the polynomial, your program works in a certain number of steps. Each step computes a new variable, an intermediate variable from the previous ones. That's one equation. So you have an implicit polytope for every program. So this can be used. Those will be polytopes with maybe even 3 points each. It's not clear if this will be easy to compute mixed volumes, but it is possible in principle.
Yes, Baron.
So suppose I have a p-adic chip, or black box, that can do p-adic arithmetic really, 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 really well.
Yes.
Would you use it? What's the first thing you would do with it?
I would try and design a unbreakable code.
In this context.
Good.
Where do you see a potential for p-adic methods rather than numerical? I mean, how complex?
So what you're trying to do here is you're trying to set up a system of equations. So as I write this system down, I haven't implicitly told you where my x's or t's come from. This really is a system of equations, and you pick your favorite field that you want to do the computations over. If you think in terms of the homotopies, then I have to have some kind of continuity properties to be able to track my system. But this is really just a system of equations that hopefully define some curves. And if I can do p-adic arithmetic on these...
You're doing a dynamic, you're running a dynamical system.
Absolutely.
So if I can do p-adic dynamics...
Exactly. So if you want to, x sub 1 is a solution of here, and then my dynamics says that my Jacobian, not this, inverse times. Anyway. So if you use the dynamics, you have to have continuity of t. So t here has to be continuous. And then you can sort of use nice kind of lifting methods to approximate and lift.
By the way, there is a master thesis by Paul Briding. Well, he transferred some of these things in this Smale problem context to the p-adics. But locally, everything is very nice, even nice in the complex numbers. But there is a global problem because this is totally discontinuous. So somehow this idea of homotopy somehow breaks down. So.
Yes, absolutely.
The Berkovich notification.
Yes.
Maybe we can talk about it. Yeah.
Yes. Any other questions? Sorry for going over time.
Do you actually do experiments with these things as well? Or
Sorry?
do you actually code them up and...
Yes. Sorry, the people that know me are laughing.
And you don't run into issues like, chaotic paths and
Oh, it depends on.
He's asking about chaotic paths.
Yeah, it depends on how you set things up. And so I've done experiments sort of, in the general case, and there everything is nice. But then also for particular systems you have, what's the best homotopy? How do these paths behave if things go off to infinity? Do they come close together? So conditioning is a major problem. So if I have paths that come close together, how do I correctly track between these two things? How do I design homotopy so my paths are far apart so that I don't have ill conditioning nearby? These are lots of experiments that I and others have run. And the nice thing is that, well, you can design homotopies which come close together. You have to use higher precision to be able to see that they're separate, and design algorithms to be able to handle these things. Yes?
But once you adapt the precision, are you probably able to say that you have a correct answer because you have used the correct precision?
So I'm going to, I believe it was a recent paper by you and Mike Shu to do provably adapt the precision.
Probably adapt.
So what's currently... He doesn't even know what okay. So implemented in my software, Bertini, is a heuristic adaptation of the precision.
With Latin and background?
Yeah, there are new certifiable ways to...
Let I answer like this. You fix a precision, you can do the calculations and prove you have an approximate root. If you have an exact root and it is non-degenerate, you need a certain precision to get to that point. And that precision is estimated and well understood. It depends on the condition number at that root.
So
if the root is well posed, no problem.
Well posed in the sense that it's exactly a floating point?
Non-singular.
No, it's a non-singular. The exact root is non-singular with respect to
the condition number is something related to the norm of the inverse of the derivative. There are a few corrections there, but it's essentially that.
So in principle, it's possible to do numerical algebraic geometry in a way that your answers are provably, your answers are proved by your running. Yeah. When you run the program, you have it.
if your endpoints are non-singular.
If your endpoints are non-singular in the sense that they can still, they can't converge, so you have to start with the correct number of...
In the sense that if I have a generic, a sharp homotopy, where the number of start points is equal to the number of endpoints, I can provably guarantee that I have all of the solutions here. They're all distinct. Everything is.
But if the paths do merge, then you.
How do you? So the notion of approximate root means I'm in the quadratic convergence zone of Newton's method. So if it's a singular point, what does the quadratic convergence here mean? You have to come up with a new definition of how do I approximate this root. Do I give you a deflation type algorithm where I remove the multiplicity and now prove that that was the right way to remove the multiplicity here?
I suppose, so I guess what I'm trying to understand is looking at the size of the coefficients and the degree of everything.
Yes.
Is there an obstruction to doing numerical algebraic geometry to probably get
the obstruction is the root separation bounds are whatever they are, exponential or doubly exponential. That is the fundamental
What is your
barrier.
input? Is your input real and complex numbers or
Integers.
Coefficients?
well, input has to be integer coefficients.
That makes a difference because with real and complex numbers, you have a surface of imposed system. If you have integers, in principle, if it is non-degenerate, the condition number will be smaller than a certain bound. And if it is degenerate, well, you can still do calculations with precision.
Okay. I suggest that we continue the discussion over lunch.
And so, especially for computer scientists interested in matrix multiplication and stuff like that, there'll be some very basic algebraic geometry at 5:10. Soda.
Yeah. Yeah, thank you. It's got a nice
You've got a nice. I don't think cross H.
Sorry?
For G cross H. Yes. That's proof doesn't work.
Well, I got it. On the average, will not. But in particular examples, so on the average, things are well separated. You might be able to do